All right, everybody, we're back at it again with another video. This time, I'm going to show you how you can retrieve millimoles of titrant at your different quarter pH values for, I believe this is prompt B4. So from the plots of the titration of histidine and water from graph 1, make a new table that includes pH range 1 to 12.5 and a value of titrant millimoles for each quarter pH unit. And then you'll be able to do the water titrant subtraction from the histidine buffer titration, and just to get the histidine alone titration. So what I need to do is make one column here. I started another new sheet here for my workbook. And I carried over the combined titrations, the two rows of titrants that, or sorry, the two columns of titrant data that I used to make my graph, carry those over into the new sheet as well, just so I can show you what I'll be doing. And I recommend you still work with this. Negative is for hydrochloric acid, positive is for KOH. It's really funny how the math and the signs still work for the titrants because of this whole strong acid, strong base disassociation, that you can just basically assign the acid a negative number and the base a positive number. The math still works out perfectly fine. So what we're gonna do is for every single, we have to first make this pH 1 to 12.5. And so, like I've always said to everyone, let the Excel program do your work for you. You don't have to go down the entire line and type 1, 1.25, 1.5, 1.75, 2, 2.25, all the way until you get to 12.5. Chances are you're probably going to make a mistake, but if you at least focus your attention on the first like 5 or 6, you can highlight this. And if it's a well-observed pattern, meaning if Excel can figure out that you're going in 0.25 increments, if you highlight this, you can take the bottom right little square that pops out next to the highlight, and then just drag this, and Excel is literally going to follow the same pattern that you provided for it. And I'm just gonna drag it down until that little box next to my cursor comes up to 12.5, which is right there. And that's it. I have my entire pH row, or column, I should say, filled with the pH values. I'll go ahead and add 2 significant figures, or make sure that I have 2 decimal points for the pH values. So I'll just go ahead and shift around these 2 buttons until I get my 2 decimal points for every single pH value. Simply what you can do is just copy the value for the corresponding titrant for each pH that you end up seeing for the curve. So here in this column, it is my histidine buffer titration. That is going to come from these values over here. Actually, I should just put this into green because water reminds me of blue. And then the water titration millimole values will come from this column over here. So first I asked myself, do I have a pH value of 1 represented in my histidine buffer titration? I do, luckily enough. I'm going to just basically take those millimoles of titrant, copy it, and then just move it over. Do I have something close to 1.25 on the pH? Yep, I got something right here. 1.24, that's pretty close. In terms of proximity, anything within 0.05 in either direction pH units, you're more than welcome to just kind of like copy those titrant values without having to use the graph to estimate. So I just keep on doing this activity over and over again. I'm looking for 1.5. I got like 1.51 here. I like that. I'll go ahead and copy that. 1.75. I got a 1.74 right here. I'll copy that and paste it over. But what if and I kind of saw this pH values. Okay, so we have something over here in the histidine buffer curve. We have a pH of 6.98, a measurement at 7.13, and then a measurement at 7.48. It looks like we got the 7 covered and the 7.5 covered, but we don't really have a titrant value that is close enough to 7.25. So now I have to hunt for this one using the graph because there's no estimation here that would end up giving me an accurate titrant value. So I'm going to be looking at the histidine curve for a 7.25 titrant value. And the way that I'm going to do this is using the actual histidine curve here. Now, I actually, for this exercise, I do recommend that the vertical and horizontal axes cross each other automatically, that they do not, you don't have anything funky because it is going to come up a little wacky. So what I am looking for is something at around pH 7.25 for the blue histidine curve. Now that is going to be in this area over here. Now, the thing is, I probably shouldn't be zooming into the graph, and there's only so much zooming in that I can do on Excel before essentially I can't estimate any further. At the same time, if I zoom in far enough, I might be able to see one axis but not the other, and that's just going to defeat the point of getting a good estimation. So the trick that I have for you is, if you can't zoom in Excel, just zoom in the graph. And again, I don't mean like using the actual zoom function. What I want you to do is, again, we're trying to zoom into the 7.25 pH region for the histidine titration. I will take my y-axis, I'm going to just move over to the left a little bit, and I'm going to double click the y-axis. And I'm going to say my bounds for the x-axis, I want the minimum now to be 7 and the maximum to be 7.5. And when I do that, I pretty much now can see the 7.25 very, very precisely for the y-axis. But what about the x-axis? I want to get kind of as a precise approximation as possible. That's kind of like an oxymoron because you're either approximating or you're being precise, but you know, it's weird being both. I want to get a as accurate value or as precise value as possible. So it looks like my relevant titrant values are going to be somewhere between 5 and 10 millimolar of titrants. So likewise, I'm going to double click on the x-axis. And for the bounds for the titrant, I am going to change the minimum to 5 and change the maximum to 10. And when I do that, now I have this like really super zoomed in representation of this part of the curve that I can make a much better estimation as to how much titrant you know, it corresponds to pH 7.25 here. And if I wanted to, I could just basically eyeball it right here. So if this is this value here, 7.5, and the one over to the right is 8, at 7.2 for pH of 7.25, I can just kind of like move my cursor all the way down here and just keeping everything proportional. I'm probably at about 7.8 perhaps in terms of the titrant, which is a really good estimation. Looking back at the data, I said 7.8. You know, I don't know how we would have gotten to 7.8 just using these numbers here, but I can go ahead and just do that for the millimoles of titrant at pH 7.25. Notice I was already in the positive region for the x-axis. So I want to keep that number positive as well. Same if we were in the negative region, then we want to keep the millimoles of titrant negative as well. But I said 7.8 was like my estimation. For other areas that you're not really sure on how to estimate, if you want to get in as close as possible, now you know, you can kind of like keep on finicking and changing the x-axis to zoom in further and further and further. Maybe we can change the y-axis from 7.2 to 7.3. And it looks like now the more relevant x-axis millimoles of titrant is going to be between 7.5 and 8. So I'll double click the x-axis, change that to 7.5 to 8. Now I'm kind of like doing a little bit more work than I probably should have for this, but I could even be more precise. At a pH of 7.25, it looks like my curve actually intersects at 7.85 millimoles of titrant, which is pretty impressive, all with the help of these like minor grid lines that I have here. And I will go ahead and just basically put 7.85, be a little bit more precise, 7.85 for the millimoles of titrant. And so you can just use this little activity to hone in on the missing pH values they have. This is actually particularly useful for the water titrants, because remember, water has no, or DI water has no buffering capacity whatsoever, and those small amount of titrants really shift your pH in the beginning to acidic or basic pH values very, very quickly. And so you want to make sure that, like for example, adding 250 microliters of titrant here of KOH shot my pH to about 10. I'm missing all of this data here, but if I just, zoom into these regions on the curve, I should be able to get better approximations of the amount of titrant at these different pH values. I'm going to take one quick second right now and just populate this data as these columns as best as possible. All right, so I filled out the rest of my columns with my titrant data. Again, I'm leaving the hydrochloric acid titrant as negative and the potassium hydroxide titrants as positive. Note that because of the lack of the data points from our water titration, we can't go below 2.75 for the pH, and we can't go above 12.0 for the pH. So those we have to leave blank and leave alone. If at any point you also too didn't reach, the extremes for that, for your water titration, just leave those blank as well. And the correction can only happen for the columns in which you have both a histidine buffer titrant and also a water titrant as well. So simply what I'm going to do is, now that I have the histidine buffer titration column first and the water titration column second, I will ask Excel to subtract the water from the histidine buffer. So I'll say equals, highlight my histidine buffer titration cell for a corresponding pH, subtract, and then the corresponding water titrant cell. And then essentially just drag that out for the other end of the values, making sure that I don't report anything for data that I have missing. So now it looks like I'll only have a corrected titration curve between pH 2.75 and all the way to 12. So on the basic side, we're fine, but it looks like we're going to not capture that first carboxylic acid pKa. But in any case, what I'm going to do is, now for the corrected graph, I'm going to insert another graph with dots and scattered dots with smooth lines and markers. I'll select my data and add a new series and call this the corrected histidine titration, or histidine alone titration. And the X values are going to be my titrant values, which I'll just highlight here on this column over here on the right side. And then my Y values are going to be my pH values. I will remove that equals 1 preset that it has there, and then just highlight the corresponding pH values. And when I do that, I have my corrected histidine titration curve. It looks a little funky because it is. I didn't acquire that much TF data for the acidic side, but essentially what's happening is we can see here that I have my the second pKa2 for the imidazole ring, and then pKa3 is over here for the amino group. And if you compare this to the titration curves, the uncorrected titration for histidine, where it starts to plateau off in the upper region and the lower region, that's due to the buffering now of the water. Those are the pKWs that you're seeing there on the top and on the bottom. So when you correct for this, those pretty much end up disappearing and they end up just turning into simple equivalence points. Here I'm stopping at this equivalence point at around pH 4, between pH 4 and pH like 2 or something, or 3. And so I'm not capturing the other, the first pK, the pK of the carboxylic acid group from histidine. So I can't, this is a rather incomplete and sad looking corrected histidine titration. Hopefully everyone else was able to capture a lot more data than what the TFs did 2 years ago. But yeah, you should end up looking, getting something that looks a little bit like this, and you should be all set for capturing titrant values at different quarter pHs and doing the actual titration. Again, don't forget for the x-axis to denote that negative values equals the hydrochloric acid titrant and the positive values equals the potassium hydroxide titrant.